We have learned how to determine where the function is increasing or decreasing. So now we can use that information to locate the local extremer. So that means the local maximum or the local minimum values. So here let's look at a graph. So this way is called a first derivative test. We use the increasing or decreasing informations to get the local extremer. So now let's look at this graph. Okay, this graph, and we know this would be the local maximum, right? This point gives you the local minimum. So you can see on this part, on the left side of the local maximum, which is increasing function. So the derivative is positive, right? So here is positive. Then here is negative, right? The derivative is negative on the right side of this point. Then this will give you a local maximum. And here, the derivative on the left side is positive, negative, right? Decreasing, then increasing. So this is the positive. So this will give you the local minimum, right? So this is called the first derivative test. So the first derivative test says first derivative test. It says let C be a critical point of the function f of x, then if f prime changes from positive to negative at C, which is this case, right? Then f of C is a local or relative maximum. If f prime of x changes from negative to positive at x equals c, then f of c is a local or relative minimum. Okay, so here the test says C must be a critical point. Okay, if C is not a critical point, we don't care about that. The reason is, which is the following theorem, which is called the Fermat theorem. The Fermat's theorem says this C must be a critical point. It says all local extrema or local maximum or local minimum only happens at the critical point. We have no other choice. Okay, we have no other choice. So this is the reason here at the beginning we must have C is a critical point in the first derivative. The reason is the Fermat's theorem says the local extrema only happens at the critical points. So now let's use the example. Let's use the example we discussed in the increasing or decreasing function. That's this example you have seen before. I just write down again. Right. So since we want to locate the local extrema, so we have to, because the local extrema only happens at the critical points, so we have to take the derivative, right? So this is 3x squared minus 29. So which is, if you factorize it, so here I just go through quickly because we have took this one already. And we set, since this one exists everywhere, so we just only can set this f prime is equal 0. So you have 3 times x minus 3, x plus 3 equals 0. So you have x equals 3 and x equals negative 3. These are the critical values, right? Then we still need to determine the increasing or decreasing. So this is our number line. So we locate the critical values on the number line. This is divided into 3 parts, right? So the same thing, we need to plug in a negative number on this interval from negative infinity to negative 3, which is negative 4. You can plug in negative 5, negative 6 as you want. Then you will see this one, if you plug in negative 4, so this is the negative, this would be negative, so it's positive. So this is positive. So on the whole interval here, which is positive, right? So we know this is increasing. And here we plug in 0 on this interval from negative 3 to 3. Then you will see this negative. So on the whole interval here from negative 3 to 3, this is negative. And so it's decreasing. So then this is the, from 4, we plug in 4, the derivative will be positive again. So here is positive, so this is the increasing on this interval from 3 to positive 3. Okay? And so we know this is the increasing, then decreasing, right? Decreasing, then increasing. So at negative 3 would be a local maximum, right? And the 3 at 3, which would be a local minimum. So this would give you the, we can see by the first derivative test, f of negative 3 is a local maximum, and f of 3 is a local minimum. Okay, so now let's look at another example. So this is the example, f of x equals 1 minus x to the 2 over 3. So we still need to find the critical points. So we take the derivative. We use the what? We use the chain rule, right? 2 over 3, that's 1 minus x to the 2 over 3 minus 1. So this is the outside function, the power 2 over 3. The inside function is 1 minus x, so we'll take the derivative times the derivative of 1 minus x. So this would be negative 2 over 3, 1 minus x over negative 1/3. So negative 1/3 that means 1 over x minus 1 minus x to the 1/3, right? So this would be times 1 over 1 minus x to the 1/3. So we still need to look at the derivative, the critical points, right? But we notice that this 1 never be 0. This derivative never be 0 because the numerator is non-zero, right? So, but we still have we can still find the critical point. The reason is when x equals 1, the denominator equals 0. So that means when x equals 1, this f, the derivative at 1 does not exist. So this is also a part of the definition of the critical points. So we can get conclusions that x equals 1 is a critical value. So we only have one critical value, so we still divide our domain for this function. Locate this 1 here. We divide our domain into 2 parts, right? On this part, which is from negative infinity to 1, and this part would be 1 to positive infinity. So here we plug in what? Plug in the number less than 1, so we plug in 0, for example. Then you test plugging 0 to here. Then you will see it's a negative number, so it's negative here. So on the whole interval, this would be negative, so that means it's decreasing. And then on this interval, we plug in 2, for example. We plug in 2. Then you will see this would be a positive number. So on this interval, which is positive, so that means it's increasing. So we know the decreasing interval is from negative infinity to 1, and the increasing interval is from 1 to positive infinity. So we can see by the first derivative test, so it's decreasing, then increasing. So this would be a local minimum. So by the first derivative test, f at 1 is a local minimum.